So, very welcome to the third speaker, Friedrich Solowjow from Aachen, so from RWTH, and his talk is about event-triggered learning and similarity of dynamical systems. Please.
Thank you for the introduction. It's a great pleasure to present here. And my presentation is about the question of when to learn in the context of dynamical systems. So, the goal is to consider the question of when is learning necessary to derive resource-efficient algorithms, which fits nicely in the context of this conference. So the term dynamical system is heavily overloaded, and since this is also an interdisciplinary event and many communities here are coming together, we are considering this question a little bit in more detail, and I'll try to go through the details, what problems I'm actually considering, and what you should imagine if I talk about dynamical systems. So as a rule of thumb, think about engineering system, robots, or biomedical processes. And these are mostly things that move around, and they depend on their past. So they can't just teleport through space. They need to somehow evolve, and they have like this autoregressive structure. And additionally, there's usually actions and control inputs that we can apply to the system. So think of this robot here that's illustrated. And now we apply a control command to one of its joints. So there's the input that it should move. So the next thing that happens, the robot moves. This is what we want. These are the kind of systems that we're interested in. Now, if we abstract this a little bit, we introduce this dynamics function f, which takes as input the state of the system, which is this robot here, and the control command that we apply. So this is the motion that we apply to the joint. And what we get in the next time step is the next state of the system. So the robot has moved. This is what this dynamics function is doing. So if we now abstract one step further, we have this function that gets the state, the control, and what we output is the next state. This is the kind of systems that we're interested in. Now, the problem that we want to solve is the first one. We want to do forecasting. We want to predict if we have a certain state. We have a sequence of actions that we apply to the system. Then, what will happen to the system? How will it evolve? And this can be solved by learning this function f, which is usually unknown. This is physics, and we can observe data from the system. But in most cases, we don't know this f exactly. So that's the first problem. We want to learn the f. Very closely connected is the control problem. So we have this robot, and we want to make it move in a certain way. Of course, having this dynamics function helps here, but here the goal is we want to find a sequence of actions u that drive the system to some goal state. And now, additionally, there's the fault detection problem, or looking for anomalies, where we compare properties of the system. We want to figure out if something is different than usual, or if there are anomalies that we need to deal with then. So you might think there are algorithms that can solve this from classical machine learning, like finding anomalies, for example. But the problem of looking at dynamical systems is different. And here with this simple example, I want to illustrate what's going on here, which makes this particularly interesting. So usually we assume we have independent data that is identically distributed. And here we look at this two-dimensional normal distribution. I've outlined the contour plot. It has zero mean and some variance sigma. Now let's look at some samples from this. So 1, 2, 3, 4, 5, 6, 7, and 8. And they look like they come from this distribution, which is true here, because this is how we set it up. It's like IID. So this is the standard problem that we usually have. These points, they fill out the distribution, and they randomly appear somewhere. They do not depend on the sample that we had before. Now, if we look at learning for dynamical systems, then this is different. So here, this is the simplest dynamical systems that you can imagine, where we have linear dynamics, so this general function f that we considered before. This is now a matrix, or two matrices, A and B. And if we set this up correctly and choose A, B, and the variance of the process noise W here in a certain way, we can actually achieve the same stationary distribution for this dynamical system. So this is nice. So data should look similarly, right? So now let's imagine we just initialize this somewhere based to the stationary distribution, and now we let the system evolve. And now you can see, due to this autoregressive structure, the next point is actually close to the previous one. And it doesn't jump through the whole distribution, it only moves a little bit. And this is now the data that we need to work with. And now the question is this data that we observe from this dynamical system distributed accordingly to the stationary distribution? And the answer is no. And this is a problem, because this is the data that we use for learning eventually. However, there is a solution. We also have this control input u, which we can use, and we can choose it. And what you usually do in systems theory, you apply some wild motions to make this robot move around. For example, this first one, which is pseudo-random binary, or these sinusoidal signals, and they make the robot arm move wildly around. So you explore the whole distribution, and you create nice data, which is helpful for learning. Of course, depending on this function f, the sinusoidals might work well. However, in general, this is not the best solution, and we've looked in previous research on how you can do this optimal, which are the other control signals that you can apply that optimize for points that are extremely helpful. And bottom line is, this works. We can create nice data to learn, and then at some point we're done, and then we can stop learning. And then if you think of this robot arm, when you learn, you move it around in all kinds of wild motions. This is not what you want at the end of the day. It should pick something or do a certain task. And this is where most research stops, and we say, we're done. We've learned something, we can use it now, we're happy. So in my opinion, this is not the end of the story, because there are a lot of potential changes. If you think like of changing temperatures, tear and wear in the system, vibrations in the environment, all of this can actually have very huge impacts on the performance of your system. And of course, learning is the answer. We can relearn and adapt. But how do we do this? And this is the core of my research, which leads now to this question of when to learn and event-triggered learning. What we want to do is we want to detect these changes, relearn, and then stop learning again, which I generalized here in this block diagram, which I'm going to step through you. Of course, the idea of using data, learning models, and being adaptive, all of this is not entirely new, and I want to be a little bit more precise here. So this is the classic approach. You have a model, you do something with the model. And on the left-hand side, you have your learning control system. So this is the robot arm. And you can use the model to synthesize a controller. Now, when you have learning algorithms, then your learning control system gives you data that you put into your learning algorithm, and then you get a new model, which you can then use again. And now adapting to change, this has also been done. However, usually you do this exactly once in the beginning when you deploy your system, or you do this all the time, that you keep learning. And learning permanently is actually a problem when your data is not good, as you've seen like with these red circles that cluster. When you want to learn, you want to excite. And these are competitive objectives. So instead, we've introduced event-triggered learning, which has this learning trigger that considers, is what you're doing actually working? And if it works, perfect, use it. That's why you've learned. Don't do these stupid actions. You don't need the data that's good for learning. You want to exploit what you have. However, if what you're doing is not working, then you should detect this. And once you know what I'm doing is suboptimal, it is significantly different from what should actually happen, then you should go back to learning, create good data, update, and stop learning again. So this is the core idea of event-triggered learning that I want to convey here. Now let's look at an example, and here you have this stochastic linear system again, which is one of the most simplest, and we pair this up here now with linear quadratic costs, which is also the simplest thing that you can consider. And there's analytical solutions to this control problem. And here I want to highlight that the noise is random, which makes the state random. Therefore, this randomness also pops up here, which makes the cost random. And now this is a random variable. This is why we usually also optimize the expected value of it. And this is where we usually stop. We say we can optimize the expected value, we're fine. But we can also look at the distribution of this. And surprisingly, no one has done this. And we dug deeper here and actually computed the same object that we've seen in the previous talk, which is here now the Laplace transform and not the Fourier transform. And we derived the moment generating function for this cost. And why is this useful? We can compute confidence bounds based on this, which then leads this trigger. So here in the blue line, you can see the control cost. This is time. And now the green line is the change in the dynamics that we introduce. So the system changes, our trigger detects that the line goes out of bounds. Then we detect this, the red line. Then in the gray area, here's the zoom, we create new good data, update, and then we have a good controller again. So we have this adaptive thing that does the principal decision making. It looks for change, and if it finds significant change, it adapts. And this is now this core idea, and here for the signal to learn, we use the control cost. And this is a very restrictive setting. So in general, we're not able to distinguish all dynamical systems based on this. So we went a step further and looked at how can we compare more general properties. And one thing that we've looked at is comparing the stationary distribution of stationary dynamical systems. And the tool that we use are kernel mean embeddings and the maximum mean discrepancy. And here I'm going to be a little bit more technical. And the core idea is this is a metric on the space of probability distributions. So it tells you how different are two distributions. If you think of two vectors, it's the distance between them. And of course, since these are infinite dimensional objects, this is hard to compute. And now the nice property of this is we do have estimators, and we can compute them extremely efficiently, and we only need to put our data into kernels, and we do not need any more assumptions. We just put the data inside of kernels, compute this equation, and then we have an estimate of the distance between the two underlying distributions. And even better, there are concentration results for this. We know, given the amount of data that we consider and our alpha level, how close we are. And this speed of convergence, this is critical for statistical tests, but it only works for independent data. And here we're looking at correlated data in dynamical systems. So how can we generalize this now? So independence can be phrased as the joint distribution factorizes. And now we can plug this into the same metric. We can also consider the difference between the joint distribution and the product of the marginals with respect to the MMD. And now we can use this idea to quantify the dependence within a time series, within a trajectory, and we can subsample this, which makes us more resource efficient again, because we actually don't need all the data. We can use just a few data points, make these IID, and then we actually have theoretical guarantees, and we are more resource efficient. The downside is we need multiple independent trajectories to estimate this time shift. So once we have this, we can use the standard kernel two-sample test results, and then we get a kernel two-sample test for stationary dynamical systems, which is great. Now, this is another test that we've derived to implement the idea of event-triggered learning. Now, let me change gears a little and show you one of the applications that we're doing. Of course, there are these engineering applications, but here I want to highlight a different one, which is from the biomedical domain and the collaboration with the University Hospital here in Aachen. And we're looking at ECG data to detect arrhythmia. And these are also dynamical systems. So if you look at these distribution here, this is a healthy patient. and this is one patient with AF. They look different. And now if you put these into the statistical test that we've derived, they're able to tell you these distributions look different if you actually have AF. And then with high probability, you can say, you better go to a medical doctor and get your heart checked out. And with this, I want to sum up and give you a little outlook. So the core idea here is when to learn. This is the essence of event-triggered learning. And we want to test for changes. If we detect these, create useful data, and then we stop learning because we don't need it anymore. Instead, we keep testing if there is change. And if we detect this, we go back to learning. So we've implemented this for various applications. One is sensor networks, which is also relevant from the point of view to save resources, because here we were able to save 70% of resource in communication networks by learning better models when necessary. Another one is looking at industrial pumps. This is an industry collaboration where we're able to find faults and anomalies, also very similar to the heart. If there is a defect, then vibration data looks different. And also from the haptics community, there's very relevant problems where we want to distinguish different materials based on vibration data. And with this, I also want to thank Pierre-François and Paul Kruse, who are now generalizing this line of research towards improved tests via conditional distributions, and also at looking at natural changes that arise in a game theory setting, where your action actually induces change, because the other player then sees that you're doing something and changes their behavior as well. With this, I want to thank you. Happy to take questions.
Thank you. So are there questions from the audience?
Hi, I take the opportunity again. So Barbara Hammer from Bielefeld. Thanks for the very useful, insightful work. So I wonder if you have not a rapid but a smooth change, so something which is damaging and you know you should act quickly because otherwise this will be too late if it's like critical infrastructure. So what would you do? Because so far, if I understood correctly, it's more for rapid changes, right?
So very good question. So I would argue it also works for smooth changes, and it works once you have a significant difference. So also depends on what you change. If it's, for example, the cost signal, and you have smooth changes on your parameters of the system, you will detect this. And if this is just a smooth change in what you actually care about, then it's small changes. And if these are small, then the test will ignore them, because they could also be caused by random fluctuations. But once these changes become significant, then the test will tell you, okay, something's wrong here. So you also don't overfit to small changes. You only relearn once this is actually significant.
Okay, then it's probably a question of how to set the threshold. So because you have the time window and which is clear. Thank you very much.
Exactly. Thanks.
Hi, thank you for a super interesting talk. I had a couple questions. First is, I guess I just
state your
missed the
name and
crucial-
your affiliation.
Sorry,
just shortly.
Yeah, sure. Yeah, okay. I'll do it in the middle. It's fine. Yeah, my name is Victoria. I'm from the University of Osnabrück in Germany, doing a PhD there. So yeah, coming back to the question, I missed the crucial point somehow when you said about the detecting the changes, like changes in what exactly, and like how you measure it. Is it like a feedback from the environment, the state of the environment? Yeah.
So also very good question. I need to go here. So this is the critical part. You need to define a statistic. This is something you care about. Yeah. And I've shown two examples here. One is control cost. So how well is your system performing? This could be something that you use for changes, to detect changes on, if this behaves as you want. Or we also put the stationary distribution of the system in there. So we check how it behaves in space if you plot your states. These are two potential things that you can test on and look for changes there. But you can also use different things, and we have also done this, for example, on intercommunication times. And in general, you can put anything in there that you actually care about. This is the thing that you want from your system. that it should behave in a certain way, and this is what you design statistical tests for, and which is often non-IID.
Yeah, thank you. Can I have a quick follow-up question as well to that? Yeah, I can't help but like think of it in a context of reinforcement learning, and somehow really want to define it in terms of finding some action, value, function, or whatever, and use a reward as like this measure. Is it possible? Like, can you think of your system in this paradigm?
So this actually ongoing work where we're combining these
Okay.
ideas with reinforcement
so-
learning, and where you use your reward signal as an. This is what you can plug in here.
Yeah,
This is your reward.
that's what I was feeling all the time. But like, it didn't sound like. Yeah, you never said the reward, and I thought, okay, maybe it's.
No,
just,
you
I
can
don't know,
also
seems
do
like
that, and
Okay,
we're
that's-
trying
that's
currently,
great.
and
Yeah,
ongoing work.
cool. Thank you.
Thanks.
Hello, and thanks for the inspiring talk. Actually, my question was asked. So yeah, it was about using the reward and yeah, in the learning algorithm using the reinforcement learning, because you talk about changing the environment. So it come to my mind why then we shouldn't take care of getting some signals like reward and punishment if there is, I mean, a direction. So let's say semi-supervised learning kind of. Therefore, yeah, I don't know if you have any more comments for that.
So you can also set it up differently, and you can also test on your transition probabilities. You can check if your MDP is behaving in the way it should. This is also like a totally reasonable object to test on. At the end of the day, it depends on what you want. So if your agent, it can still have the same reward, but it somehow behaves differently now. If you care about this, then it is totally fine to test on the dynamics as well.
Definitely.
But at the end of the day, if you just wanted to have a certain reward, you don't care what it's doing, then use the reward to test on.
Okay.
And this is still like an ongoing question that like we're banging our heads against this. What's the best signal to actually test on? Or is there a best signal? I don't know.
Yeah. Yeah, exactly. Do I have time for this? Yeah, just because this question was asked, so I
I'm
then
sorry,
we
we have to move on.
Yeah.
So otherwise, you can also take this offline.
Yeah, let's do
Thank
it offline
you.
then. Thank you.
Thanks again.